Okay. Hi, everyone. Good morning. This is week 6. Today, we are going to look at sequence modeling, self-attention, and transformers. Have you looked at the homework yet? You had? Okay. So if you have questions, you can post it on the class, I believe. But maybe I did not enable the forum. I will do that. Or you can email me. Both are fine. So sequence modeling today, but last week we looked at the recurrent neural networks, and this was the basic update equation. You know the meanings of x, h, theta, and f, right? Hidden state, input, model parameters, and model. At the end, this arbitrary length input is mapped to the hidden state of the network. So it's a lossy compression at the end. We also looked at major CNN architectures. We looked at residual networks. We looked at normalization layers, batch norm, group norm, and then types of convolution. We also discussed why vanishing or exploding gradients problem happen. It was the result of this repeated matrix multiplication, which happens through the successive calls to the RNN, and also happens with multiple layers stacked on top of each other, this repeated matrix multiplication. And then there were two solutions for the exploding gradients problem. You need to clip the gradient magnitude if it's larger than a certain threshold. This is a hyperparameter of the method. For the vanishing gradients problem, we introduced this gating mechanism, and these were implemented through LSTMs, long short-term memory networks, and also GRUs, gated recurrent units. Because our lecture is about sequence modeling today, it's mostly about self-attention and transformers, but to set the context for it, we need to start with RNNs and model sequences using RNNs. So it would be very useful to remember what RNNs are doing. So inference in an RNN goes like this. We have a sequence X. This could be a sentence. This could be a sequence of pixels or patches, but it's a sequence, right? It's indexed by a time variable t. Now, this is processed by RNN, and it has, parameters. So parameters theta, so parameters theta are, it was UVW, and then there's also this hidden state H, and this is what we called an RNN. And this outputs OT, which is an output element at time t, but crucially, it also outputs a hidden state and feeds it back to itself. That's the major difference between MLPs, CNNs, and RNNs, because we have now a feedback loop. If you remember the update equation of this, So HT is equal to a nonlinearity. We can use a sigmoid here. W times H previous hidden state plus current input. Right? This was the update equation for the RNN, which updates the hidden state. And then based on this hidden state, it can optionally output something. It's all. Again, a nonlinearity. This time we are using another matrix multiplied with HT. Of course, you can have bias terms here as well, plus B, but I didn't show it. Doesn't make it too much of a difference. So this is the inference in RNN. And we said that this type of modeling can cause vanishing or gradient, exploding gradients. And that's why we introduced this idea of gated RNNs. And LSTM is a type of gated RNN. GRU is a type of gated RNN. And the idea here is to pass the previous hidden state intact to the next time step. That's the idea here. So if we draw that again, let's say we have the same sequence, x t minus 1, xt plus 1. This is a sequence. This goes through the gated RNN. Now we have parameters, more parameters. So U, V, W as usual, but also extra parameters for input and forget gates. We still have a state. Okay. And this still outputs OT. So it's the same, but here again we have HT minus 1. But if you write the update equations, we now call this H tilde T, which is the usual, like the regular RNN from the left. So W times H T minus 1 plus U times X T. And then the next state, the true next state, is a combination of the forget gate multiplied with the previous state plus input gate multiplied with the H tilde, which is the new state. Actually, the final new state is this, but it is calculated over an intermediate H tilde, which is the same as the plain RNN. So this one and that one are the same. And through these gates, so this forget gate is actually implemented again as a function of previous hidden state and current input. Similarly, this input gate is WI H T minus 1 plus UI X T. So this is the summary of RNN and the gated RNNs. Yes? Where? Mm-hmm. Here, You can use it twice, or if you want, you don't use it because there is already a nonlinearity. I guess it's a design for your neural network. Yeah, it won't hurt if you don't use this second sigmoid here. Through these gating mechanisms, which are written here, F and I, it is possible to pass the previous hidden state unchanged to the next time step, and that's the difference, fundamental difference between standard RNN and gated RNN. It's like the residual connection idea, ResNet idea. Okay, so this was just a recap of RNNs and gated RNNs. Today, we will start with sequence modeling. Actually, we already talked about sequence modeling in RNNs because here, this is a sequence, input to the RNN. These are sequences, right? So we are actually doing a sequence processing. But we will talk about it in more detail. We'll talk about character level language modeling, and through that, tokenization, token embeddings or token encoding, and word level language modeling. Also, to get the best of both worlds, we will talk about subword tokenization, such as byte pair encoding, BPE. And then sequence-to-sequence encoder-decoder models, and we will study this in, for example, machine translation, which is translating one language to another by a model. That is what Google Translate does. And we will actually look at Google Translate's model they used around 2017. So we will look at the translation model that they used in 2017. And then from there, we will gradually make changes and then arrive at the attention mechanism, self-attention, and then finally transformers. And today, as you might know, all AI models that you are using today, from ChatGPT to, I don't know, your favorite image generator, video generator, everything is based on transformers. And this is actually the last major type of architecture that we will see in this class. We have seen MLPs, CNNs, RNNs, and transformer. That's the last. So actually, we don't have a new thing after transformers. Okay, this is like Mount Everest right now. Well, actually, some researchers are saying that the recent state space models like Mamba are actually doing better than transformers, but we can discuss it later. I'm not really convinced about that. But yes, transformers are the most recent, latest architecture that are being used by all major AI models, whether it's language processing or vision processing, whatever. Transformers are now the best architecture we have so far. This week, we have a recommended reading, which is this Unreasonable Effectiveness of Recurrent Neural Networks by Andrzej Karpathy. This is a blog post from 2015, but you are highly encouraged to read it if you did not already. It talks about character level language modeling and shows the power of RNNs. Even if you model things at the character level, you get amazing results. So after we look at the sequence-to-sequence encoder-decoder models, why is there a blank page here? Okay, I think I will talk about sequence modeling here briefly. So what does a sequence mean? It's a sequence of data, and a sentence could be considered as a sequence, right? For example, the sky is blue is a sentence, is an English sentence, and you want to process this using a model. First, what you need to do is to discretize its elements, right? And I can, for example, take each word, which is separated by a white space or a punctuation mark. I can take anything in between as a token, okay? So these are, let's say, tokens. So this is tokenization. Why is it not? So tokenization, let's say these are x1, x2, x3, x4. And then we are going to encode these tokens, token encoding, and then we will obtain vectors that represent these distinct tokens, and we will call them token embeddings. Okay, so this is the overall picture I'm talking about here. There are different types of tokenization methods. There are different types of token encoding methods. But conceptually, from your raw input data to these discrete entities is called tokenization. Similar thing in images, you can do it by, let's say this is your image, and you want to process this using a transformer, a vision transformer. What you need to do is to patchify this first. Now you can think of this patch as a token, and then you want to encode that sub-image, that small patch, and then get a patch embedding or token embedding. Okay, so different modalities, language and image are different modalities, but the same logic is followed here. We first tokenize our sequence, split it into its discrete elements, and then encode each element, and we get the token or patch embeddings. After that, you process this sequence by your model, and it could be a sequential processing. So your model take E1 first, do something, and then it consumes E2 next, do something, E3, E4. Or your model can take E1 through E4 as a whole, all together, and then do some processing. That's also called sequence modeling. So after that, in that processing, when you get this vector set of vectors E1 through E4, you can apply attention mechanisms so that the embeddings, token embeddings, can talk to each other and they affect their embeddings. So one embedding affects the other token's embedding through the attention mechanism. And an architecture that uses the self-attention mechanism is called, we call it transformer. So briefly, self-attention is like a kind of a layer in neural network, like a convolutional layer or a fully connected layer. You can think of self-attention as another type of layer. And it's the most important module of a transformer. And transformer is a kind of a neural network architecture introduced in 2017. And transformers have replaced LSTMs, RNNs in NLP, and CNNs in vision. The illustrations below, so the first one is illustrating attention between two sequences. So let's say the one on the left is the input sequence, this one, and the one on the right is the output sequence. A token in the output sequence is affected by all elements in the input sequence, and this is called attention. So the token in the output sequence is set to attend all elements in the input sequence. If you apply attention within just one sequence, so there is no distinction of, so above here, we have an input sequence and output sequence, but here we just have one sequence. And you apply attention within that sequence, and it's called self-attention. This is self-attention, okay? And here, each element, for example, this one, gets affected by all other elements. And the same is true for each of the tokens. So this is, they affect each other through some key query value mechanisms that we will talk about, and they affect each other, they modify each other's, update each other's embeddings. So this is like a global overview of what we are going to discuss today. Transformers made a huge impact in not only deep learning to the world, huge impact to the world, and this was the footsteps of this was actually was felt in early 2020s, and if you look at the number of publications which used transformers was increasing exponentially from 2017 to 2021. Archive publications as well. And then the key papers which introduced transformers is that Nurik's paper, 2017, Attention is All You Need. If you look at its citation graph over the years, it also follows an exponential trend. And today, it has more than 200,000 total citations, and only in 2025, it's more than 50,000. So its impact is huge. This is the original transformer paper introduced for the language modeling. In 2021, this idea was adapted to images, and vision transformer was introduced in ICLR 2021. This also has a huge impact in not only in academia and research, but also in industry and in general. So 76,000 total citations and 25K of them in this year so far. So transformers have made a huge impact to the world. Okay. So to set the scene before transformers were developed, let's start from character level language modeling. The problem here is we are given a sequence. It could be a partial sentence or a word. And the task is to predict the next character. Remember, people, when talking about ChatGPT today, they say that, oh, it's just next word prediction, next token prediction. Yes, that's right. And its origins are coming from here, character level language modeling. We are given a sentence or a word. Now the task is to predict what would come next as a character. And here's an example. The sky is B question mark. What could come here? You can guess that it's probably the sky is blue, and the letter L, the character L, will be coming to there. And this is the task. So to solve this task, we first as I said, tokenization our sentence. And character level means we tokenize the sentence into its characters. So it becomes a character array. Each character now is a token. And each token can be represented by a one-hot encoding. And this is not the only choice, but it's practical. It works, it's practical. Why is it practical? Because the number of different characters in a language is finite. In Turkish, we have 29. In English, 26. Even in Chinese, it's a finite number. And maybe not, I don't know. But if you also add the punctuation marks, the set increases, but it's manageable sizes. So you can use a one-hot encoding. The letter A, for example, in your one-hot encoding will be 10000, right? The letter B will be 01, and all the rest will be zeros. So, and this is called token encoding or embedding. And this is a very simple, actually the simplest type of embedding we can do, because we are encoding each distinct character with a one-hot vector. Now that each character is represented by a vector, now I can run my RNN on top of this and model the sequence, right? And this is what is being done here. It is a code snippet taken from that blog post I recommended as reading. This is a Python implementation of a standard RNN. Here we define the step function, which is like taking one time step, one step of processing at a time step. It's very simple. It takes the dot product between the input x with its parameter wxh, and then it's taking the dot product with its self.h, which is this hidden state, right? This is the hidden state. It is multiplied by another parameter whh, and then sum together, pass through another nonlinearity, which is tanh, and now the hidden state is updated. And output is hidden state times another parameter. And as your friend pointed out, there is no nonlinearity applied on top of this, but you can, or you choose not to, as done here. So it's a very simple implementation of a standard RNN. You create it, you instantiate it like this, and then you take a step by calling this line. If you call it repeatedly, you make several time steps, right? Remember, in RNN, we represented RNN like this. It's the xt current time step input at current time. We call this feedback connection, and we drew this black square which represented a time step, and through here we have h hidden, and here we have ot, right? This is implemented in this simple Python code. And this simple code can do amazing things. First, a very simple example. Let's say we are trying to model the word hello using a set of tokens of just 4 characters. The first character will be represented by this one-hot encoding, 1000. This will be processed by the RNN. It updates its hidden state based on the parameters, these W parameters. And then it will output a 4-dimensional vector where you can take a softmax of this, and this will give you which character is more likely to be outputted here. And then it turns out that here, the second letter, which is E, has the highest logit. If you apply softmax here, you will have the highest number here. And if you randomly sample through this probability distribution, you probably get E, and that will be outputted by your RNN. And in the next time step, now the next input is in the word hello is E. It will be processed by the RNN. This is the hidden state. And then it outputs the OT vector, which is the logits over your set of tokens. Again, you apply softmax, and this time the ideal output, which is for L, has a low value, right? But ideally, if you want this RNN to model the word hello perfectly, then we want this L to be high, all the others to be low. And this is the job of the loss function. You apply the loss function, which can be cross entropy here. The label for this time step will be 0, 0, 1, 0. And you apply cross entropy, back propagation through time, and then it will adjust the weights of these parameters so that this entry will be increased and the others will be decreased. This simple model can do, why is it not going there? Let's see. I want to show you examples. Unreasonable effectiveness of RNNs. This simple model, when trained on, let's say, Shakespeare poems, it can generate poems that look like written by Shakespeare. I'm not a Shakespeare expert, so I will just skip this, but let's look at the Wikipedia article. They trained it on this 100 megabyte data set of raw Wikipedia articles, and they trained this character level RNN, and look at the output that this simple model gives. It looks like a Wikipedia article. Of course, the contents are garbage. If you read it, it's not. But at a surface, from a surface, it looks like a Wikipedia article. It can do markdown links, right? Some kind of markdown markings. Here you see a link, but I don't see the closing parentheses. So see there is an opening square bracket, but you don't see the, or maybe is it this one? I don't know. But yeah, it looks like a Wikipedia article. It can also create the headings, table of contents. Sometimes it generates valid XML. If you train this on a geometry, LaTeX source of a geometry textbook, it can create compilable LaTeX code, and then the final PDF looks like this, looks like a paper, and so on. They also trained it on Linux source code, which is open source, and it can generate this valid-looking C code, as you can see. But of course, it's probably garbage. But you can see the footsteps of ChatGPT here, right? It can create one token at a time, and then it looks like it is doing something. Of course, ChatGPT is now much more advanced and much better. But this is character level language modeling. Any questions so far? You can do, similarly, a word level language modeling. So you can model the language at the word level, not word level. And here we need to represent each word with a fixed dimensional vector, and we will call these word embeddings. Can we use one-hot encoding to encode words? What do you think? It will be too long because the number of distinct words is probably huge, right? I think in English it's 175,000. I remember a number like that. In other languages, maybe it's much different, but it doesn't make a lot of sense to encode each word by a one-hot vector because you can always have new words. You can always have, for example, in Turkish, you can add a suffix to the word and you get a new word, and maybe you encounter some out of vocabulary words. So word level modeling has its disadvantages, but it's possible. You can do it. And in fact, an influential model called word2vec proposed in 2013 did this. It was using, it started with one-hot encoding and then arrived at a sensible embedding, which we'll talk about now. So yes, it's you can do it. Today, word2vec is not being widely used because we have better word embedding methods. But this is influential and historically very important. You should know this. So we will briefly look at word2vec now. Given a word, word2vec produces a fixed length vector. That means it embeds the word into a finite dimensional space. And the nice thing about word2vec is it tends to map semantically similar words to nearby points in the vector space. Let's see how it does that. So you start with a corpus. Corpus is a word for data set in NLP. So it's like, let's say you downloaded all Wikipedia pages and concatenated them into a single text file. That becomes your corpus. Okay. So it's a huge text data set. You basically form context word pairs from your corpus. And context means here words nearby. Okay, if I take a word at a certain location, its context is neighboring words. And you can set the context window. If you set it to 1, it's just the next word or the previous word. If you set it to 2, next word and the previous word. So this is your context. And you basically train a neural network which predicts the context word from the central word or the other way around. You predict the central word from a context word. Okay, both ways are possible, but this is the idea. Word and context, which are nearby words, and you try to predict one from the other. There are different methods. One of them is called the skipgram. There is also continuous bag of words. Skipgram predicts the context word from the target word. Now let's give an example so that it's more clear. Let's say for the sentence, the quick brown fox jumped over the lazy dog, and for context window n is equal to 1, here are the word pairs. For the word quick, you have 2 context words, the and brown, and you list them here. For the word brown, you have quick and fox, and so on. Okay. Yes? Yes. Yes. And I will talk about it. They initially used one-hot encoding, but from there, they will learn a more sensible and less dimensional encoding. So, okay, we formed this context word pairs. Now, what do we do? In this specific model, which is called the skipgram model, and here you see a context window equals to n is equal to 2. So the model takes the input word and tries to predict the context words, right? And to do that, you maximize this probability. Probability of observing word t plus j, given that we observe word t. I will show how this can be done with neural networks in a couple of slides later. But these are the two models they use. So the other way around is also possible. You can predict the central word from the context words. Okay, you give a context word and then it predicts the central word. And here is the algorithm to train the word-to-vec. First, we obtain a corpus, a large text data set. Second, we list all unique words in this corpus and represent each unique word using one-hot encoding. Okay, so up to here, it's straightforward. Unique words, one-hot encoding. As you can imagine, this part will be huge, because if you take all the Wikipedia articles and list all unique words, you will get hundreds of thousands of words. So this input vector, one-hot vector, will be a very large dimensional vector. Next, we present context as input. So now we can look at the right-hand side. At the input, we have the context word. And at the output, we want to predict the central word. Okay, and here we are inputting the one-hot encoding of the context word. And the network here has this softmax layer, which will predict the word out of all possible words. And in between, we have a hidden layer. It's a linear hidden layer. We train this with all the context word pairs, and this neural network is trained. Once the training is done, this part, the weights in this part will give you here your word-to-vec model. You can discard this part. It's not needed. Now, after training is done, whenever I give a one-hot encoded word to this shallow layer, it will give me an embedding vector, an encoding, which is 300 dimensional here. So notice that the input vector is very large dimensional because it's as large as the number of unique words, and in this case, 10,000. You are mapping them into a 300 dimensional space, and now this vector is no longer a one-hot vector, but it's probably dense. It's densely populated, but it's an embedding of your word. This is word-to-vec. Because it worked, you can do more complicated things, of course. Probably it wasn't necessary. I don't know. Here is another implementation from another paper, but this is still word-to-vec. You give this one-hot vector in the input layer. There's a reduced dimension hidden layer. And then at the output, you predict either the context or the word from the context. And this representation in the hidden layer is your word-to-vec embedding. Now, nice things emerge out of this word-to-vec embedding. It's somehow surprising also. But if you take this huge, I guess this was Wikipedia data set, and then do this word-to-vec modeling, and let's say you had this 1,000 dimensional word-to-vec embeddings. If you want to visualize them, you can project them using PCA into 2 dimensions. And here is what it shows here. So PCA projected 2-dimensional vectors. If you plot country names and their capital cities, you see that there's a relation there. The countries are here, the capital cities are here, and the difference vector is kind of similar. So it turns out that this model actually puts the semantically similar things near each other. And then the offsets are also meaningful. If you take the average of these difference vectors, and if I put a new country here and add this difference vector to that country, it will probably point me to the word-to-vec embedding of the capital city. So this is interesting. Another visualization is similar thing, but here it captures the gender relation. The difference vector between a man and woman and uncle and aunt and king and queen, they are all similar. And if you take the also plural, singular plural relations are also, so queen, queens, king, kings. This red vector, difference vector, is also encoding the singular to plural relation. So it's very interesting properties. And because of that regularity in the difference vectors, you can do simple algebraic operations like addition and subtraction. If I take the word-to-vec embedding of biggest and then subtract the word-to-vec embedding of big and add the word-to-vec of small, it will give you the word-to-vec embedding of smallest. So it's very interesting. Take France, subtract Paris, add Germany, you will get Berlin. And so on. There are more examples in the table, but this is word-to-vec. Okay? We can take a 10-minute break now and meet at 10:45. Okay, so far we looked at character and word-based models. We looked at character and word-based tokenization. Now we can compare their advantages and disadvantages. In the character level tokenization, the advantages are obvious. First of all, it's simple and language agnostic. You can have character level tokenization for English, Turkish, all languages using the Latin alphabet, and also other alphabets. It's straightforward. The number of characters are finite. It can handle unseen words or misspellings naturally because you are not indexing each word, each unique word. Useful for morphologically rich or low resource languages. But the disadvantages are when you break the sequences into its characters, your sequences get much longer, and this introduces higher computational cost. And then it becomes harder to capture long-range dependencies and semantic meaning. Those are the disadvantages of character-level tokenization. On the other hand, word-level tokenization gives us shorter sequences because we break the sentence into its words. It becomes a shorter sequence. So faster training and faster inference, those are good things. And tokens have clear semantic meaning because they are words, which improves the interpretability of the models. Disadvantages are You have a fixed vocabulary, cannot handle out of vocabulary words. Sometimes people invent words or misspell them, and those become out of distribution, out of vocabulary, and that's a disadvantage. And requires a large vocabulary for multilingual or morphologically rich language such as Turkish. This increases model size. As you know, we can, from a root word, we can add lots of suffixes and you get lots of different words. And that's a different thing than English, for example. So both these things have advantages and disadvantages. Can we do something better? Can we use the advantages of both approaches? The answer is yes. And it's called subvert tokenization. It uses the best of both worlds. There are many subvert tokenization methods. The most famous one is byte pair encoding, word piece, unigram modeling, sentence piece, among others. Here we will look at byte pair encoding, and the others are also has a similar logic. We are looking at BPE because it's the most widely used tokenization today. In fact, I believe ChatGPT is using this tokenization. Also, CUEN, open source models like CUEN. You can go and check this CUEN tokenizer. It's okay, it's not here. Key concepts, yeah, it's in the documentation. If you click on the tokenization, it explicitly states that it uses byte pair encoding and gives some details as well. In its dictionary, token dictionary, it has 150,000 tokens in its vocabulary. This is like, you know CUEN, right? It's one of the recent China-based model, which is really good. And because it's open, lots of industry, lots of companies are actually taking CUEN and then adapting it to their own needs, and internally are using CUEN. So it's using byte pair encoding. ChatGPT also, they say that they use it, but most of the details are closed there, so we don't know what exactly they are doing, but yes. So byte pair encoding, let's learn what it is. We start with, again, a corpus and a desired vocabulary size. Okay, we decide on some vocabulary size that our model can handle. And as you have seen for CUEN, it's 150,000. I believe for ChatGPT and similar models, it's around a similar number. But yes, we have a training corpus and the desired vocabulary size. We start with listing all unique characters as the initial dictionary. So this is like character level encoding. This is our initial token set. Next, we tokenize the corpus using the current token set, which is the characters, all unique characters at the beginning. After we tokenize our whole corpus, we find the most occurring token pair. So we look at which two characters occur the most in our training corpus. Then we take that character pair or token pair, merge them, and create a new token out of those merge. And we add it to the dictionary, and now we have an updated new token set. Now, if the size of the dictionary I have is at the desired size, then I stop. Otherwise, I go to step 2 and repeat. So very simple idea. You find the most occurring token pair, you merge them, and it becomes a new token. You add it to the dictionary and repeat. For example, Here's an example. I took it from Hugging Face. Suppose that our training corpus consists of these words. Of course, this is a toy example, a designed example. In our corpus, we have the word hug. It appears 10 times. There is the word pug. I looked it up. It's a kind of dog, pug, puppy, some kind of small dog. It appears 5 times. Pun appears 12 times. Bun 4 times. Hugs 5 times. Okay. And we initially start with our initial vocabularies, which is the number of, which is all the unique characters. And these are, as you can see, B, G, H, N, P, S, U. Now, what do? We tokenize our corpus using the token set, which are all characters. And then we find the token pair which occurs the most. And in this case, the pair UG occurs 20 times. Why? Because it appears 10 times in the word hug. It appears 5 times in the word pug. And then in the word hugs, 5 more times. And in total, we have 20 appearances. That means, and the other pairwise appearances are less. So we add this new token UG to our vocabulary. Now we have this vocabulary. Notice the addition from here. This is new. Now using this new vocabulary, we tokenize our corpus again. This time, the word hug is tokenized by H and UG because now we have the UG token. We don't need to do the U and G, but we use this longer token to represent this word. P, UG, PUN, BUN, H, UGS. Now, what is the most frequent token pair in this tokenization? UN, right? Because we have 12 times here, 4 times here, it's 16. And all the other pairs are appearing less. Okay, yes, it's UN. Yes, this is new here, 16 times. And then using the new vocabulary, we tokenize the corpus again. And what would be the next merge? What would be the next token that occurs the most? Let's look at that. I think it's hug because hug is appearing 10 times here and 5 times here. So it's total 15. And all the others are less. So yes, it's hug. And finally, so this is the new token here. And finally, we have this vocabulary set, but you repeat these steps until you reach your intended vocabulary size. And we started from the individual characters and converge into this token set. Okay, so this is byte pair encoding, which is used by all the major LLMs. And here I encourage you to visit this tokenizer from OpenAI. Why cannot I go there? Okay, let me go there because it's interesting. If I say, oh no, I should use this browser, sorry. So OpenAI tokenizer, yes. So here they, You cannot see. Yes. This is an OpenAI tokenizer page. Here they show how their several models, and they use GPT-4o and 4o mini. You can also check the other older models. I think right now in deployment they have GPT-5, right? If I'm not mistaken. So this is also old, but tokenization is probably the same. So what you can do here is you can enter some text and then see how ChatGPT or GPT tokenizes things. So if I, let's say, copy this text and put it here, um, it's an English text. Below, you will see how it is tokenized. As you can see, it's almost like word level tokenization. You see each distinct color. I'm not sure if you see the colors, but it's like each different word becomes a token. But this is byte pair encoding. If you have a large vocabulary size, and if in your training corpus, English is like the dominant language, or you have lots of English words, yes, you can capture words as your tokens because they merge together, and each of these words turns out to be appearing frequently in your corpus. But if I write a Turkish sentence, let's say, you will see the difference now. Let's say I write benim adım and see how it tokenizes it. See, it splits each word into some pieces. So it shows that in their training corpus, English is more dominant because you see all the English words a token by themselves, but these simple Turkish words are split into two. Huh? Yes, yes. Yes, I'm not saying that this is something bad or good. This is just what it is. I think this just shows that their training corpus is mostly English. If you write another language, I think it will also split that. But this could be an advantage for the suffix languages, agglutinative. I cannot pronounce it. They also give some rule of thumb at the bottom of the page. Roughly 4 characters of text for common English text correspond to 1 token here. So, yeah, this is just a rough guideline, but I think for non-English languages, this is your tokens are less than 4 characters on average, as we can see here. Okay. Any questions so far? Yes.
If a word can be represented by multiple byte pairs, for example, PU is pair, G pair, and PUG pair. Which one will be decided?
We take the longer one. For example,
I mean, it is equal, like PUG, PUG, for example.
But it's not equal. If you tokenize PUG into PUG, you have 3 tokens.
No, PU.
Oh, okay.
For example, not like this one, but.
So you're saying that, let's say, in our corpus, we have PU as well?
Yes.
And UG as well. That's a very good question. Could this happen? Let's think about that first. Of course, it could happen, right? Because the token pair PU can happen, can occur in other parts of the corpus.
There are multiple
Yes, yes.
So PU becomes also there.
Okay. Then how do you tokenize, for example, PUG, right? So in our corpus, let's say we have P, PU, and UG, and also G. How do you tokenize PUG? Yeah, I don't have, I don't have the 100% correct answer. I'm not sure. I don't know. But my guess is we process this from left to right. And when I start with here, I think I would take the longest token first. So I think this would be PU and G. That's my guess, but I don't know. Huh? Yeah, maybe. I mean, if the corpus is large enough, then such a thing won't happen, maybe, but I don't know for sure. Yeah. Can we test it using the tokenizer that I showed? Is it possible, do you think? But there we don't have access to the vocabulary size and vocabulary list and corpus. So, but yes, this is a good question. So if multiple tokenizations are possible, I think the tokenizer has to choose some convention and stick to it, right? And if it consistently uses that method, then it would be fine. So I think this would be PU and G. That's my guess. Yes, there should be a deterministic choice. Otherwise, it's all garbage. Yes.
There are some verbs that can be split from somewhere. It takes a different root and different suffix. But if it's split another way, it has different root and different root suffix. And they are semantically different. So it may be helpful for.
So the comment is that if we split a word differently, different splits have different meanings because a word might have a root and suffixes. But my answer to that is this is purely data driven. There is no concept of root or suffix here or prefix. This is entirely data driven. There is no language information given in here. So this algorithm, whatever it finds, it finds. So it doesn't care about the root of the word, whether the split is correct, whether it's a valid syllable or not, it doesn't care about that. Okay, so now we have an idea of how we can break up our sentence into tokens and how to embed them. Now we can do a sequence modeling. Sequence to sequence, encoder-decoder modeling, and the best example for that is machine translation. That means translation between languages by an automated model. Around 2015, 17, Google Translate was using this specific model that we are going to talk about now. It consisted of two RNNs, one encoder RNN and another decoder RNN. And this model, which has two RNNs, it can map arbitrary length input sequence to an arbitrary length output sequence. It takes a sentence in source language from X1 to XNX. So that NX is the length of the input sequence, and there is no constraint on that. It's arbitrary. It can be 1 or, I don't know, 100. It can map that to an output sentence, which is also arbitrary length. This is ny. And the best example for that is the machine translation or speech recognition, but we will go over the machine translation example. We said that there are two RNNs. Input sentence is fed to the encoder RNN here in the upper part. So encoder or reader RNN reads and processes the input sentence. And then the encoder RNN emits or outputs the learned context C, which is here. This is the output of the encoder RNN. And as you can guess, it is the last value of the hidden state vector. What does it do? It read the entire sentence token by token. And at the end, the hidden state actually is a compressed summary of the input sentence. It's a lossy compression, but it's a summary of the input sentence. And then the decoder RNN or the writer RNN takes this C as input. So if you see this here, it takes that C and then produces the output sentence, the output sequence, token by token. In this case, word by word. They use word level tokenization. And this is how the model works at a very high level. The two RNNs are trained jointly to maximize the average probability of observing the correct output given the input over all XY pairs in your training data set. So that means your training set consists of source language and the translation in the target language pairs. That you have such pairs, and you should have a lot of them. And you train this using the usual backpropagation, gradient descent, and so on. Typically, this context vector, as I said, is the last hidden state of H and X. So that means in this RNN, the last step, which the last step processes the last token, which is X and X. And this is the H and X, the hidden state, after when we tokenize the last token of the input sequence. Yes?
Say that we have two very small languages that are not used very often. How am I going to achieve this process to encode and decode? Because they will be solvable.
So, okay, the question is, if you want to train a translation model between two low resource languages, we call them low resource. There is not enough data. And there are many such languages actually. That's a very good question. It's a research topic. How do you deal with low resource languages? It's not easy, and the models will overfit. You know, it's not, you have just limited number of pairs. There is a paper from Google, I forgot which year, but around 2018 or 20. They deal with the low resource languages by mapping them first into a common latent language, and then taking the translation out of that. That common latent language does not have a human meaning. It is discovered by the model through training of multiple languages. They said that the translation between high resource language pairs helped the translation of low resource language pairs. But again, this is very high level information, but we have to look at the details, but that's a very good question.
And can we use the English as a, say, middle step?
Yes.
For this translation?
Yes.
Like Turkish to English and then some other.
I think they also tried that. Yes. I don't know how it compared in terms of performance, but yes, this is something that they tried. Using English as the common translation medium. Yes. So around 2017, before Transformers, well, Transformer paper was published in 2017, but it took some time for the industry to adapt it to production ready products. So in 2017, Google Translate was specifically using this sequence to sequence architecture. So we have sequential processing here. We have a English sentence, he loved to eat, and then this is translated into a German sentence. And the encoder RNN processes the sentence word by word. Each word is first embedded to a word embedding. You can use word2vec or any similar model to that. And then your word embeddings are fed to the encoder RNN as input. And encoder RNN takes each token, word in this case, one by one, and it processes its internal hidden state. And then at the end, it outputs this S, which is the last hidden state. This is what the encoder RNN summarizes for this sentence. The decoder takes this S and then produces the output sentence word by word. They used LSTMs as the RNN encoders here, and this was proposed in 1997. Okay, I talked about these. Okay, the problem with this kind of specific architecture is that, can you guess the problem here?
If the sequence is long,
Yes.
the summary will not.
Exactly. If the input sequences gets longer and longer, because S is a vector, and you are summarizing a long sentence into that fixed dimensional vector, that is the bottleneck. And as you can see in this plot, as the sentence length increases towards right, the performance score, Blau score, which measures the translation accuracy, the higher the better, it goes down with sentence length. I'm just asking a question myself. Why is it low here? And I don't know the answer. Does anybody know? Why is it low for short sentences?
Maybe there is not enough context.
That could be, yes. Maybe there is not enough.
But we also design
Design of the glove. Okay, yes. You also said? Okay. Yeah, it's probably because of the design of the glove score. But anyway, the important thing here is the performance gets lower with the increasing sentence length. So what can you do to overcome this problem so that the encoder and decoder works better for longer and longer sentences?
Instead of making a lossy compression,
Mhm.
you have the context on one.
Yes,
A single.
exactly. The solution is to build this context as on the fly as we output each word here, and that's exactly what is called attention. Okay, so now let's look at attention. So the attention mechanism is when you are producing the next word in your output decoder, So let's say you are producing this word here. Now the RNN here is going to, well, the example is not drawn for that word, but it's drawn for this word. This RNN will take an attention vector, which is actually a context vector, which has access to all words in the input sequence. So that's the key difference. Each word in the output sequence now has access to all words in the input sequence. And it can use the embeddings and hidden states in the decoder at any time step it wants through the attention mechanism. Let's show the attention mechanism here. So this AI is the attention vector which goes to here. Okay. Now we are looking at a situation where we started with the start of sequence, let's say. It created the first word, and now I use that word. Now I'm trying to generate the second word. I'm trying to generate this one. At this point, this RNN here, it has access to the attention vector AI, and this AI is a weighted combination of the hidden states over all tokens in the input sequence. In fact, AI is, as shown here on the bottom left, it's a weighted average of XTs, and XT is the encoder hidden state vector. So it's a weighted sum of encoder hidden state vectors over all input tokens, and the weight PT is calculated by this softmax over ST, and ST is the attention function which takes an output token and an input token. So it takes a pair of output token, input token, and calculates something. For example, similarity. Well, it doesn't say that what it calculates, but it's an attention function and it's a MLP. So it's a neural network. Attention function takes a word from the output sequence, so the I-1 word in the output sequence, and it takes a word in the input sequence, compares them somehow, it's an MLP, and then returns a scalar value. That scalar value determines the weight of the combination. And then when you train this on your data set, the attention function is learned, the network learns it. So the optimal attention function is learned through the task, through the data set. Okay? And when you do that, you solve the problem. Look at the this performance here. Previously, it was like this. For sentence length more than 20, it goes down. But now, for sentence length for even 60 words, now you keep the high performance going. And this is the success of the attention mechanism. The tokens in the output attended each token or each and every token in the input sequence. This is attention. So any questions here? Make sure you understand. Attention is just a weighted sum. Weights are determined by pairwise similarities as measured by the attention function, which is an MLP, which is learned through gradient descent. And that's it. This is the summary of attention.
Like,
No, it's not a pre-trained function. It is learned. I believe it is initialized randomly from scratch with small numbers. Yes.
What was the purpose of the null parameter?
The purpose of the null parameter is it's a special start of sequence token. So you need to signal the decoder RNN to start working. Now start producing a sentence. There are lots of special tokens in sequence modeling. There's an end of sequence token. There's a start of sequence token. If you look at the CENG tokenization documentation, you will see such tokens. Modern LLMs also have question starts token, question ends, answer start, answer ends, chat starts, chat ends. So there are lots of special tokens. Okay, so the attention solved this problem, which is nice. And then to further improve the performance, they added bidirectional encoder. So remember in the previous slides, we only have this forward LSTM. Now they added backward LSTM. Now each input sentence is now modeled from left to right and right to left. You can do this because you already have access to the input sentence. Now this made it better. To represent each word, you now have hidden state coming from the forward LSTM and the hidden state coming from the backward LSTM, which captures the previous context and the future context. So for this word, for example, you model this context and that context through forward and backward LSTMs. And then this makes it better performance. And on top of that, they make the RNNs or LSTMs deeper by stacking lots of LSTM layers on top of each other. And then the whole system looks like this. You have a bidirectional LSTM, which models the input, and then you have lots of LSTM layers. So basically the depth is increased to increase capacity, and the whole system for Google's machine translation in 2017 looks like this. And it was not bad. It was doing an okay job. But then when transformers were deployed, it was a much bigger, a significant improvement. Okay. Yes. Mm-hmm.
The attention only encoder and decoder, right?
So in this multi-layer encoder LSTM, attention mechanism is here again at the end, which so the attention takes a weighted sum of the hidden state vectors. The only difference here is that hidden state vectors are calculated by many, many layers, not just one layer. That's the only difference. The attention mechanism is the same.
There is no attention to the state.
No, there is no attention between the hidden states. No. Attention is between a token of the output and all hidden states of all tokens in the input. So the attention mechanism was also used in computer vision in 2015. For example, in the image captioning problem, you give this image as input, and then CNN processes the image, extracts features, and then it feeds to an RNN with an attention over the image. And it finally produces this caption, a bird flying over a body of water. And if you take each word, it is and highlight which parts of the image it is affected by. You see these attention maps. For example, the bird word highlights this part where the bird is, and this word highlights all the other places. So attention has started to go into computer vision in 2015. Okay, But this still has a problem. Even if we use a bidirectional encoder and many layers and we get a good performance, there is still the problem of sequential processing. Because this is sequential processing from left to right in the forward LSTM, from right to left in the backward LSTM, this takes time. And how can we remove the dependency on sequential processing is the question. And the answer is yes, by using self-attention. You can parallelize the training using self-attention, but let's start fresh to self-attention after the break, 10-minute break. Let's meet at 11:30. 11:40, sorry. Okay, at the beginning, I said that self-attention is kind of a layer in a neural network, in a transformer. And here is why I say that. So if you think of self-attention as a neural network layer, what it takes is a sequence of vectors at the same time, and then it outputs updated vectors. Let's call them y, 1, 2, and n. So it takes vectors x1, x2 through xn, does something, and then outputs y 1 through n. As in the attention mechanism, it is doing nothing but a weighted sum. Okay, self-attention is also a weighted sum. So that means yi is actually a sum over from 1 to n, a weight for ith input and jth output, and xj. You can think of it like this. It's taking a weighted sum. How are the weights calculated? That's the important part. So wij is a softmax over some relation between xi and xj. So that, remember the attention function, which was implemented by an MLP in the attention mechanism. In self-attention, we have this function f, again, learned by a neural network. And this is yes, so this is self-attention, but now we will make some final touches, and we will introduce key query value concepts. Now, overall, we are taking a weighted sum, a weighted average, but we don't want to use the vectors as in their raw form, but we want to use their so-called values. And by value, we mean, so how can I do this? I'm going to delete xj and write something else. Let's say, so here, I'm going to multiply xj with a matrix, and this is called the value. As you can guess, the matrix WV is learnable. So it's a learnable parameter of the self-attention module. Similarly, I can write down this f function which compares inputs xi and xj using their again learnable parameters wq and wk xj, and this is called the key and this is called the query. So from each element in my input sequence, I extract three things: key, query, and value. They are extracted by learnable parameters, wk for key, wq for query, and wv for value. And then I take the weighted sum of the value vectors weighted by wij, and wij is the softmax of dot products of query and key. So this is the whole mechanism. This is self-attention. You understand what's going on here, right? No? So what's happening is that we have n vectors in the output and n vectors in the, so n vectors in the input, n vectors in the output. And here, each of them interact with each other and they have an updated vector after self-attention. So they modify their values through the self-attention. So for example, yi here, a specific output in the output is a weighted sum of everything in the input layer. And weights are determined by the pairwise relations, xi, xj. That's it. And what does the f do will depend on the task. If this is a machine translation task, if you are training this self-attention or the transformer which includes this self-attention for a machine translation task, this f or its learnable parameters, wq, wk, will learn certain parameters. But if it's another task, it will learn another parameter. So it will learn the optimal parameters to solve the task. So here is everything written nicely, the same thing. Questions here? Self-attention. In the attention mechanism, we have two sequences, one in the output, one in the output. The elements in the output attended all elements in the input. But here, in self-attention, there is only a single sequence, and the attention is applied within the sequence. That's why it's called self-attention. It's very easy to implement self-attention. We take in a tensor x in, and first thing we do is to extract the query, key, and value vectors by multiplying the input vector with the Q matrix, K matrix, and V matrix. And then to compute the output values one at a time, we take the query, take the dot product with the key of the jth element. This gives us a relevance. Remember that f function in the slide. And using that relevance, we normalize them using softmax, and using the normalized relevance, we take the weighted sum of the values, and this is the output at location I. This code doesn't work and isn't intended to. The goal is to explain how attention mechanism work. It is deliberately not vectorized to make it cleaner. Okay. So this is the code, and in figure illustration, we show the self-attention module as here. The query and key enters to matrix multiplication, and scale them. Masking is optional. We didn't talk about it. There is softmax, and then we take again the product of value vectors and the weights. And this is the schematic illustration of these equations. So it's the same thing in self-attention. Query, key, and value vectors can be collected in three matrices, Q, K, and V. And then you can express the self-attention using this compact mathematical expression. So far, I did not show you this part. It's the scaling part. So the query key multiplications are scaled by the square root dimension of the key vector. It is done in practice, and here's an explanation from the transformer paper why they do that. They basically talk about for larger values of decay, the dot product grow large in magnitude, pushing the softmax function into regions where it has extremely small gradients. To counteract this effect, we scale the dot product by 1 over square root of the dimension of the key vector. So something that is found through practice, I believe. But even with this, it should work theoretically. But this is now the common practice to scale the query key dot product by the square root of decay. So it doesn't have a super theoretical justification, but practically they say that this works, and they point out to some numerical problems actually in their explanation. Same explanation in a longer context taken from the paper. If you are curious, you can look at it. The idea of self-attention is not actually new. It was used in other domains before, but simultaneously with self-attention in 2017, there was also so-called non-local neural networks in 2018, and this was in computer vision. Self-attention was in language processing, and I'd like you to draw your attention to the non-local neural networks, expression for the non-local neural networks. Let's look at the expression and try to see the similarities between self-attention and non-local neural networks. X here is the input feature vector, and xj is the input feature vector at location j. Y is the output feature vector here. F is a relation function, learnable function, which takes two feature vectors at different locations, and it does make a comparison probably, but it's a learnable function. Whatever the task requires, F learns that. And this F gives you a weighting, a scalar weight, which weighs this G. Again, a learnable function that computes representation. For F, they use this dot product parameterized by, again, two theta and phi functions. Overall, this is similar to the value in self-attention, and here it's query and key. So contemporary developments, one in language domain, the other in vision domain, non-local neural networks and self-attention are exactly the same things, actually. And if you look at the illustration from the non-local neural networks paper, you see that it's very similar to the self-attention figure that I showed you. X goes through three functions first, and these are the key, query, and value functions. Key and query are multiplied first, passes through softmax, normalized. So we have normalized weights here. Normalized weights are multiplied with the value, and then summed together, we have the output. Exactly the same. So I'm really curious about whether these two groups have any communication between them before publishing these. So I don't know the history or the background, what has happened, but two very similar developments. One was published in NeurIPS 2017. The other is CUPR 2018, but basically the same idea. Both of them got lots of traction, adoption, but this one took, as I said earlier, 200,000 citations, but I believe this one also has tens of thousands. This also is very impactful. But it goes even back to 2005. The idea is not new. Taking this weighted sum of embeddings of the elements in the sequence is not new. There is an algorithm called non-local means, and this was proposed for image denoising. So you are given a noisy image, and the task is to denoise the image, so remove the noise. And to do that, usually what you do in image processing is that you apply a smoothing filter, right? Which is a local operation, which takes actually averaging in a local neighborhood. That's what a smoothing filter does. And the noises get smoothed out, but you also lose some detail. In non-local means, the idea is drastically different. Now it's not a local operation anymore. You do the denoising or smoothing using globally, not just local information, but you get information from other places in the image. For example, to denoise this patch, this locality here, you use the same size of patches everywhere in the image. So you use this patch, that patch, that patch, even this patch. So every patch is included. Now, you compare these patches, and as you can see, this one and that one are not similar. If you look at the visual content, they're not similar. So if they are not similar, then this patch does not contribute a lot to the denoising. But look at this patch. It is very similar to our query patch. So I'm trying to denoise this one now. And this is very similar to that because the visual content is similar. Now, my pairwise f function will give a high value when I pass these two patches to it. And then that means I can use this patch to denoise this patch because their visual content are similar, even if they are far apart in the image. This is called non-local means. You're still taking an average, but not within just one locality, but you look at all patches in the image. Here is the expression. Can you spot the similarities between key, query, and value? Same thing actually. So it is, this part is value, and this is a weight, scalar weight, which includes the query and key inside. So the same idea. And this was in 2005, and the self-attention was in 2017, non-local networks in 2018. Okay, now let's look at, let's compare a convolutional layer and self-attention layer. Let's say we have a sequence of input, the same sequence. What does a convolutional layer do? It has a filter, and it has sparse connections, local filter. It doesn't look at the whole thing, but locality. And here we are looking at a filter that has window length 3. So it computes according to its weights, right? Some local feature. But on the other hand, the self-attention, what does it do? It first extracts key and value vectors from each element. And suppose I'm, for the CNN, I computed the future at this location, and let me do the same for here. For the location that I'm trying to compute an output, this is my query. So query and keys are apply the dot product. And then this gives us a scalar value, which is applied to the value for that element. And these are summed together. And this is the feature at that location. But now this feature is kind of global. You see that, right? In convolution, it's local. However, depends on the receptive field of your filter. 3 in this case, it's a local computation, but here it's global and adaptive. Depends on the key and value values of all the elements in your sequence. So CNNs, we have local processing. The locality is determined by the receptive field of the filter. If you have multiple layers, if you increase the depth, let's say we have CNN layers here, and this neuron at the very top is actually affected by all the elements in the input. So it sees everything, but the effective receptive field is still local. There's a paper showing that. Even if theoretically, in a deep CNN, the last neuron sees all parts of the input, it is still local. Effective receptive field, this is important concept. But self-attention is global, adaptive, contextualized. So to the features at this location, you contextualize its feature from all other elements. You can have multi-head self-attention. So far we talked about just a single self-attention. But if you have, so this is the one in the red box is one self-attention module. you can use n of these simultaneously, and this is called multi-head attention. And each self-attention module has its own learnable parameters. And if you have multi-head attention, you automatically increase the capacity of your model. And then you can concatenate the output of these n self-attentions, and now you have multi-head self-attention. And transformer is nothing but a neural network architecture that uses multi-head self-attention blocks in its inside its processing. Of course, there are skip connections such as this one. This is coming from the ResNet idea. There is normalization layers. There are MLP feed-forward layers. But the crucial part is the multi-head attention. Here you see an encoder-decoder transformer on the left. This is the encoder part. And here you see the decoder part. And there is this connection from the input to the output decoder, encoder to the decoder. And one interesting thing you might spot is the positional encoding here, because if you do not do any positional encoding, you treat the sequence as a bag of words. There is no location information, right? But it's not good to treat the sequence as a bag of words. We need the locations are important. What do we do about them? We use positional encoding, and here is the intuition about that. Suppose that you have a sentence that is 16 words long. So each location is represented by uniquely by this binary vector. You can represent it. And then what you do is you take each of these vectors and add them to the token embedding here. Token embedding. So your final so this is token embedding. In practice, the positional encoding vectors are produced by using sine and cosine sinusoidal waves. Here you see the positional encoding vectors for up to 50 locations. So from top to bottom, this is the position on the y-axis. So zeroth position gets this alternating high frequency wave. As you go down, you get this different wave, but each row here gets a different vector. So in the 2017 paper, they showed that in two large-scale machine translation data sets, compared to the best LSTM model in that time, Transformer has produced better accuracy, but more importantly, it significantly reduced training costs from 10-fold to 1-fold. That is the real contribution of transformers on top of LSTMs because of the suitability of self-attention for parallelism. In LSTMs, you need to process the sequence, but in self-attention, each token can be processed in parallel. So summary, self-attention, all elements in a sequence interact with each other regardless of the distance between them. And output feature vector for an element is shaped by the feature vectors of all other elements in an adaptive, learnable way. Transformer is a neural network architecture that contains many self-attention modules and applies positional encoding to its input and output. And this is the summary of Transformer. So this concludes content for today. Any questions? Then we can do the quiz now.